Okay, so we are on chapter 12 here. We went ahead the other day and we kind of did the back part of the lecture officially, which was about aldehydes and ketones. So these are obviously two organic groups that have some functional groups, and the aldehyde functional group is our carbon oxygen double bond, which is sometimes referred to as carbonyl group, and a hydrogen at the end. Our ketone group is always a sort of 3-carbon run in a row where the center carbon has the double bonded oxygen. A couple of things we talked about this, which is the aldehyde group always has to end up at the end of the molecule because of that hydrogen. So it can never be inside. That hydrogen's got to be at the end. Opposite of that is this carbon oxygen double bond will never be at the end because it needs the 3 carbons in a row for it to be a ketone. So that guy will never be there. We do name these guys just like we pretty much name everything else. Again, here, the priority is the functional group in each of these cases in terms of how we would number it. But aldehydes do end in AL at the end. Ketones end in ONE at the end. So again, if we had something like this guy here, that is 3 carbons, which is based off of propane. It is the aldehyde group right here, and that would be propanol, AL. Now, in terms of numbering, we don't have anything else attached there, but this guy, wherever he is, whichever side, is always going to be carbon number 1. So are there other groups attached? You would number them accordingly, and we would put those groups in alphabetical order like we do with everything else, along with the number as to where they are located at. Now, if we had something, say, like this, we'll go there, and now, this is 1, 2, 3, 4, 5, 6, 7 carbons, which is based off of heptane. So that would be heptanone. We do need to give the location of that carbon oxygen double bond. And again, in this case, we want a number, whichever way, we'll give that guy the smallest number. And just looking at it, if you look at it going right to left here, we'll put a 3 for that guy. Obviously, if you went in the other direction, it looks like you will end up with a 5, perhaps going in that direction. And that's obviously a larger number. So we do need to put that as 3 heptanone, the 3 being where the carbon oxygen double bond's located. And obviously, again, if there were other groups attached, they would be numbered accordingly. So once you set the numbering here for the functional group, everybody else gets numbered based on that. You don't renumber or anything like that along the way here. Any questions on that there? Now, we talked about a couple reactions that make these guys. We could also do the reverse reaction, which is a reduction reaction. And in a reduction reaction, we would add hydrogen. And remember that pretty much it is the double bond here where those hydrogens are going to end up. And we will make room for it by making it a single bond. So we're just going to draw it exactly the same. Once again, going to make room for it. Very similar to what happens with the carbon-carbon double bond when we add hydrogen. It's just a carbon-oxygen double bond in this case. And we'll have that guy. That's now going to make room in 2 spots for those hydrogens. One will end up there on the oxygen to make the alcohol from which it came from. And the other hydrogen will complete our carbon there. This would make our primary alcohol here. And obviously our aldehyde. Remember that when we're writing these reactions, we want to not overcomplicate it. It is just basically one thing that occurs. It doesn't go all crazy. If we had a ketone, it kind of works the same way. So we'll make a nice small ketone here, not too many carbons. And if we added hydrogen to this, which would be a reduction reaction because we're adding hydrogen, once again, what's going to happen here is it's all going to revolve right there. Double bond will become a single bond. Everything else will be the same. And once again, now that you've made room for that hydrogen to come in, you now can put a hydrogen again, just like in the sort of double bond situation with carbon. They do go to opposite sides. They do not get added to the same sort of place. So opposite sides. That gives us our secondary alcohol, right? Which is really where a ketone comes from in this case, is a secondary alcohol. These are both what are referred to as reduction reactions. Right? And obviously, if we went the other way, that would be the oxidation reaction, taking our secondary alcohol, removing those two hydrogens and putting the double bond back on to get to our ketone. And again, going in this direction would be the oxidation reaction. Once again, removing these two hydrogens and putting that double bond back on. So again, a primary alcohol will yield a aldehyde if you oxidize it once. If you continue to oxidize it one more time, you will get a carboxylic acid, which is another functional group. So if you took that aldehyde and oxidized it one more time here. Make some room here. So take that aldehyde and oxidize it. In this case, the only difference is we're going to actually insert oxygen, and oxygen will get inserted right there. And that's going to give us the exact same thing. And just going to insert, I'll put a line under it, the oxygen there to make our carboxylic acid. Remember that if you try to oxidize a ketone one more time, nothing's going to happen. So that, as we finished up, I think, on last time, is the difference where you could use something like the Benedict's test or the Tollens test to determine whether or not you had an aldehyde that went to a carboxylic acid. And clearly those tests would be positive for those guys. The Tollens test would turn silver. The Benedict's test will turn that orangey red type of color from the copper. Changing oxidation states. Again, if they didn't turn positive, then you might have been starting with a ketone, which would not oxidize to a carboxylic acid. Any questions on any of that stuff there we talked about last time? Yeah. We're talking about this one here? Yeah, so when we're trying to assign primary, secondary, and tertiary, we do look at the carbon that has the OH group attached, and directly attached to that is one carbon. And remember that that's also a carbon that's attached to it. The attachment there, when you write it in condensed form, is the carbon is a carbon, even though the H is right there. If that was your question, yeah. So that's why it's a secondary carbon, secondary alcohol. This guy here, which is the carbon attached to the OH, would only be a primary, as it only has that carbon that's attached to it now directly. Other questions? All right, questions on any of this stuff? All right, so we sort of talked about alcohols in and out through some of our conversations. So we're going to officially go through the alcohols and some of these other groups like thiols and ethers. We've already taken care of these two guys earlier. So let's get into really these different sort of groups here: alcohols, phenols, thiols, and ethers. Alcohols, as we've been talking about, have the functional group in terms of what makes it an alcohol. It is that OH group is the functional group for a alcohol. A phenol is really also an OH group, but it has the benzene ring. So it's basically a benzene ring with an OH, a special type of alcohol. A thiol group is actually a sulfur containing group, kind of similar to the OH group. It actually has sulfur in it. And an ether is a carbon, oxygen, carbon sort of run. So you have that carbon to the oxygen to the carbon is basically an ether. Again, those are the functional groups of each of those guys, and you do need to obviously know the functional groups. And it is much like everything else, as we'll talk about, kind of where everything happens and occurs in terms of reactions, and sort of how we go about naming these things based on the functional groups. So here's each of these guys and the way that we can write them. And again, if you had something like line structure, they will write the OH group if it is obviously an alcohol. If you had something like this would be an ether, carbon, oxygen, carbon in sort of line structure. And obviously, if you had something like this, that would be obviously a thiol. So we can incorporate these things into our line structures as we've seen previously as well. So let's officially, again, talk about naming alcohols, even though I think we've sort of done it a little bit, but just officially, the IUPAC way of naming alcohols is to add an OL at the end of it. It is still based on the longest continuous carbon chain, like everything else. It does need to contain, obviously, the OH group or the functional group as part of that longest carbon chain. So our simplest sort of alcohol is really just a 1-carbon alcohol based off of methane, and that is what is known as methanol. A common name for it is what is referred to as methyl alcohol, where they can just kind of name the group, and which is the methyl group attached to the alcohol. So that's sort of where that name comes from. Ethanol here has our 2 carbons based off of ethane, and again, being a alcohol here, OL. Also sometimes named based on this group, and that's what's sometimes referred to as ethyl alcohol. Same idea as methyl alcohol. Again, they're basically the same thing. When you get to a situation where you could have more than one location for where the OH group is located, you do need to give the number for that. And with alcohols, that's approximately 3 carbons is basically where that occurs. So 3 or more carbons, you do need to give the location of the OH group with a number. So if we look at this guy here, longest continuous carbon chain, 1, 2, 3, 4, 5, 6. And we could also get 6 by going straight and up. So I'm going to take the 6 that just goes straight across here. And obviously that does contain our alcohol group in there. So 6 carbons, once again, is based off of hexane. And because it is an alcohol, it will be known as hexanol. And we do want to give the OH group, again, the smaller number. And you could probably just see it looking at this. We would go right to left, 1, 2, 3, 4, 5, and 6. That means that this would be 2-hexanol for the location of our OH group. And because I have to number in that direction, our methyl group here would be at carbon number 5. And that would give us 5-methyl 2-hexanol. Any questions on that there? This would be a secondary alcohol. As we look at it, we have the carbon that's attached to the OH, and it has 1 carbon attached to it and 2 carbons attached to it. So this would be a secondary alcohol, which if you oxidized it, would give you a ketone, basically. So we threw this guy through the oxidation. We would lose our 2 hydrogens there at the OH and this carbon, and we would end up with a ketone that looks something like this. And obviously our H2 would come off. So secondary alcohol going to produce a ketone. And once again, you should hopefully be able to see, as we talked about a number of times, not much changing other than we're removing those 2 hydrogens and putting in a double bond. Everything else is exactly the same. So once again, when you go to draw these things, you pretty much have the answer looking at you there on the paper. You just need to change that one part of it. So you should be able to get at least 99% of the molecule probably drawn just by, frankly, copying what was there to start with. Will get you the right answer. Any questions on that one there? All right, so why don't you do a couple of these guys here, and why don't you actually draw? Let's do 3-ethyl 2-pentanol. And why don't you draw methyl cyclo? Take a look. So once again, I'm just gonna go straight across here. 1, 2, 3, 4, 5. You could also get 5 by going straight from this way and then up. Will also get you 5. Might as well take the straightest one there. So our 5 is going to be pentane. And with the OH group here, that is going to be pentanol. Hopefully I didn't just write the same one we just were drawing over there. Let's see, pentanol. We do want to give that OH group the smallest number. So again, going right to left here will accomplish that. If we go the other way, we will get a larger number. That's going to be 2-pentanol. Let's see here. I think I did all right though. 1, 2, 3, 4. That's going to be 4-methyl 2-pentanol. Any questions on that? I guess that's slightly different there than that one. That's good. All right, looking at the next one, we actually have here this entire thing. Along with that, that's really sort of the functional group, and that is our phenol. So that's the alcohol on our benzene ring will be phenol. We do want to give this here now the lowest number, but where the OH group has to be carbon number 1. Which means in this case, probably counterclockwise will do that for us. 2 and then 3 going that way. And a little 3-bromol phenol in this case. Questions on that one? Yeah. It won't because it has the double bonds in there, so it's benzene. So the ring here has the double bonds, which makes it benzene. Now, if you had something like this without the double bonds, for example, that then would be cyclohexanol, and there's no double bonds in there. And if you still had that guy, say over here, it would be something like 3-bromol cyclohexanol in that case. But because of the double bonds, it makes this benzene and not a cycloalkane. And with a benzene ring and the OH, that will give you the phenol part of it. Other questions? All right, then let's draw some here. We got pentanol, so OL going backwards with our name tells us it's an alcohol and it should have 5 carbons. Now, since you're drawing it, you could put the OL, you could put the OH group there wherever you like, whichever way. In my case, I'm going to actually go left to right here. So that's going to be carbon 1 for me, which means carbon 2 would be here. And that is where I would put the OH. If you went the other way, obviously it'll be the second one in. That will take care of that part of the name. Since I chose to go left to right here, my 3rd carbon would be right there, which should have a ethyl group. And that takes care of that. And now everybody else here should just be hydrogens. Once again, to get carbon to 4 bonds. So that should do it there. Yeah. Question on that one there. All right, look at the bottom one. This is cyclopropanol, propanol, propane, 3 carbons. Cyclo means ring type structures. So I'm going to draw it in more of a line structure as a triangle. And that would be our 3 carbons. Here you can lay up the OH group at any of those points you like. I'm just going to do it straight up on top here. And that means that I really probably should have gave a number. How about 2? We'll do that. There we go. So we'll go with 2-methyl cyclopropanol. I know. All right, so that might be a little bit better. So the OH group, obviously, in this case, would be carbon number 1. So we'll go with 2-methyl to put our methyl group at carbon number 2 there. That would be good. Any questions on drawing these guys here? Cyclo just means it's a ring structure, so it's not a straight chain. So like the ends come together, and those cycloalkanes, which is really where they're based off, those are all those guys that kind of look like shapes, like the square, the triangle, you know, the 5-member there, the 6-member ring. So they're based off those cycloalkanes, where basically the ends of them kind of come together and connect and make a bond, and then they kind of make a ring structure. So that's what it means, basically. Other questions? All right, so ethanol, as we talked about, is our 2-carbon guy. It is also sometimes referred to as ethyl alcohol. It is the alcohol of alcohol, right? I suppose there. It's formed by the fermentation process of grains and sugars. It is produced by reacting ethene with a water under high pressure conditions. This is our hydration reaction that we talked about when we were talking about alkenes. Remember that when you take a alkene such as this, we're going to do an addition reaction with water, which is basically H and OH. And much like everything else that has a double bond, we're going to turn that double bond into a single bond. And remember that basically what happens now, we made room for each of those things for this addition reaction. Hydrogen goes to one, OH goes to the other, and now we have our alcohol here. So a way that you can produce an alcohol is through the hydration reaction of water with an alkene. Double bond goes away, OH goes on there. This is one of those unsymmetrical addition reactions that we talked about when we're talking about alkenes. Remember that in the carbon-carbon double bond, if you're adding something like water or HBr or HCl, that if there is a difference in the number of hydrogens in that carbon-carbon double bond, the hydrogen should always go to the one that has the most hydrogens to begin with. In this case, there is no difference. They both have 2 hydrogens, so you could put it on either side. But again, if they had different numbers of hydrogens, the hydrogen should always go to the one that had the most hydrogens to begin with. This is glycerol, which is a 3-carbon group. It has a bunch of these OH groups here. And it is very polar, those OH groups. So when we talk about alcohols that have that OH group, it is a polar bond. Difference in electronegativity, like we talked about with bonding, oxygen being more electronegative, so it's partially negative, hydrogen being partially positive. And that gives a lot of its characteristics of alcohols as being something like soluble in water. Very small alcohols that have OH groups make things soluble in water, because when you have something like an alcohol and you have something like water, which has pretty much the same bond, they are able to hydrogen bond with one another, and that makes them very soluble in water. So again, if you get a lot more carbons involved, usually around 5 or 6, the solubility starts to decrease a lot, but 5 or less carbons, usually they're pretty soluble in water because of those OH groups, and it's able to hydrogen bond really well with water. Something like glycerol, where there's like a bunch of OH groups, gives it much better solubility because there's a lot more places where water could interact with it. So having more OH groups actually increases something's solubility, because everywhere there's an OH group, it allows it to interact well with water, for example, and be very soluble. Ethylene glycol here is antifreeze, what you use in your car, right? So you don't overheat and you don't freeze, basically is what it's used for. It actually increases the boiling point of water, and it lowers the freezing point. So in case you live in a really hot area, you hopefully don't overboil. And if you live in a really cold area, your car doesn't freeze and stuff like that. Here are some alcohols, part of some plastics and stuff like that. As you see, the OH groups there. Now, we talked about making an alcohol from an alkene. Really, the reverse reaction of the hydration reaction is a dehydration reaction. And a dehydration reaction, we basically do the reverse of putting it together. So when we have an alcohol, such as this. We basically will heat it up, maybe add a little acid, and that little triangle means heat in this case. Usually if you see it above an arrow, it means heat. But we're going to basically remove the water the exact same way we put it on. So that is where the water is going to come from. The OH and the H always comes from different carbons. So they never come again from the same carbon. Just like how they go on to different carbons, they get removed from different carbons. The result of that, once again, is nothing else is going to change other than we're going to get rid of those two things. We will then make water. And in this case, we would then have to put a double bond between the two carbons where we remove the water from. So we will go from our alcohol to our alkene. So this again is what is referred to as a dehydration reaction. It's basically the opposite of the hydration reaction we just looked at. You heat it up, you take the water out, and if you put water in, the double bond goes away. Just like when we add something like water and sort of this unsymmetrical addition where the hydrogen should always go to the one that had the most hydrogen to begin with, when you remove the hydrogen and the water, the H and the OH, you actually do it opposite if there's choices. So maybe there's another carbon on the other side, and you remove it from the one that had the least number of hydrogens is where the hydrogen should come off of. So sort of the opposite rule applies than putting it on. Again, you could have a situation where maybe we'll do this here. Do stuff like that. Actually, no, we'll do. Okay, so this has the hydrogen. This has a OH group, and this guy has hydrogens. Yeah. And that guy should be single bonded would be good as well. So before I put that there, see that. All right, so. And that, all right. So if we took an alcohol such as this one here and we wanted to dehydrate it here, basically heat it up and take out that water, we are going to remove the water and we will take the OH. But in this case, we could actually take an H from the carbon to the right, and we could also take an H from the carbon to the left, right? Because they both have hydrogens. So what the rule says is in this case, we want to look at how many hydrogens each of those guys have. Guy on the right here has 3 hydrogens, right? Guy on the left here has only 2. So we would actually remove the hydrogen from the one that has the least number of hydrogens, and that is where the double bond would end up. And we would put that right here. And we would put our double bond right there between those two. They would still have their 1 hydrogen coming down. And then everything else here would be the same. So it's sort of the opposite of the rule of how the hydrogen goes on. Hydrogen goes to the most when you're adding the water. When you're removing the water, if there is an option between where you could take the hydrogen from, you should take it from the one that has the least number of oxygens. Or least number of hydrogens, I'm sorry. Any questions on that there? Okay, so got our dehydration reaction there. We talked about oxidation and reduction. Again, the definitions that we really deal with here is the gaining of oxygen as you go from reactants to products is oxidation. So oxidation, gaining oxygen, losing hydrogen as you go from reactants to products, reduction, losing oxygen as you go from reactants to products, and gaining hydrogen as you go from reactants to products. And those are the reactions that occur with our alcohols, as we've talked about, our primary, secondary, and tertiary alcohols. They can go through oxidation to get us our products. So the oxidation of our primary alcohol, which again is this carbon right here, that has the OH group attached to 1 other carbon, makes it a primary. We will always lose the hydrogen on the oxygen and a hydrogen off of the carbon. And again, we're going to make our double bond there, and that is going to get us our aldehyde group as we talked about. And clearly, as we've been talking about, we could further oxidize this one more time, and that would insert our oxygen right there, which is another definition of oxidation to make our carboxylic acid, as we talked about. The secondary alcohol also could get oxidized. And once again here, if we oxidize our secondary alcohol, which has a carbon here and a carbon here attached to that carbon, once again, we're going to take the H and the OH off and the H off there, going to put our double bond in there like we've talked about, and we will get our ketone that will occur. And obviously, as we talked about, it won't go any further in terms of oxidation there. And if we had a tertiary alcohol, which would look something like this, this carbon in the middle would make it a tertiary alcohol because 1 carbon, 2 carbons, and 3 carbons attached to it. This will also not go through oxidation as it is missing an important hydrogen here. So because it's missing a hydrogen, it doesn't have the ability to lose 2 hydrogens to make that double bond that's necessary. So a tertiary alcohol will not go through oxidation. Secondary will to make a ketone, and obviously our primary, as we talked about, will make our aldehyde. And as we talked about earlier today and previously, going in the other direction there is our reduction reaction, right? Heading in that direction. And obviously heading in this direction is our reduction reaction here, right? And that's basically the addition of hydrogen going in that direction. Any questions on that there? Yeah. All right, we talked about that. We talked about that. Talked about that. All right. Some other alcohols here. Here's an example: our methanol, again, oxidized to methanal, and then to our carboxylic acid, which, as you can see, is pretty much named the same way. It is methanoic acid. So for our carboxylic acid, we add OIC acid to the end of the name, and that gives you your oic acid, which will give you, in this case, methanoic acid. A lot of the carboxylic acids have some very common names that are used. That's sometimes referred to as formic acid, ethanoic acid, which is the second 2 carbons. Carboxylic acid is also known as acetic acid, and our vinegar basically as well. So sometimes those guys have a lot of common names that are used, and we'll get to those when we get to carboxylic acids. There's our ethanol, as we've talked about there. All right, so don't worry about that. Let's talk about this group here, which are thiols. Thiols are sulfur-containing groups. So they have this SH group, very similar to what we see with the alcohols, but it does contain sulfur. They also have a very bad smell because they contain sulfur. And these are things that are found in things like cheese, onions, garlic, oysters. They also put sulfur into gas, for example, not usually there, but they actually put it in so you can smell it when it starts leaking and stuff like that, as a way to know, like, you should maybe do something. So naming thiols, good thing. We don't worry about that. Still not going to worry about naming them. All right. But let's talk a little bit about something that we should worry about, which is a reaction that thiols undergo. So for thiols, you do need to know the functional group, and you do need to know this reaction that it does take place. And when you put basically 2 thiols together, it will, for example, if we take a thiol such as this guy, and we put it together with another thiol such as this guy, what's going to happen here is we're actually going to lose 2 hydrogens. So that is an oxidation reaction that's going to occur. the loss of 2 hydrogens. So we'll get hydrogen that will come out. And then basically what will happen is just squish everybody together. So we'll get CH3, S, S, CH3. This bond right here, where we have 2 sulfurs bonded to each other, sometimes referred to as a disulfide bond or bridge. We see those in amino acids. Cysteine makes disulfide bonds and bridges when they come together. So you do need to know that reaction. By the way, the reverse reaction would be the reduction reaction, where you add hydrogen to that and they just break apart, basically back into their own guys. Why don't you try one here? Actually, here, let's do this one. All right, what would you get if you took this guy and you added it to this guy? Oops. Yeah. And you did an oxidation. Yeah. And then if you have this guy here, and you did a reduction, draw what you would get in each of those cases. Okay, let's take a look. So sometimes it's helpful to kind of turn these thiols around so they maybe face each other. And to do that, we'll just redraw it, plus just turning this guy around. And then basically what's going to happen here in this oxidation is we're going to lose hydrogen, and that is the hydrogen is going to come out. So we'll get H2, and then pretty much we just start here and just continue to the right, take out what's in the box and connect the sulfurs. So if we just copy what's there, I got a CH3, I got a CH2, I got a sulfur. I'm taking out the box, attaching it to the sulfur on the other side, to the CH2, CH2, and CH3. Yeah. And we make our disulfide bond or bridge there. Any questions on that there? Now, if we do have a sort of disulfide bond there, we want to break it. It's really the opposite of what we just did. It will always break right there between the 2 S's. And then basically we have our 2 parts. So we'll just draw our guy on the left, which is CH3, CH2, S, and our guy on the right, which would be S, CH2, CH3. And in this case, we're really adding 2 hydrogens, which is good because that's going to allow us to complete each of these thiols by putting a hydrogen back on. So by adding the hydrogen, it basically will break that thiol disulfide bond bridge apart. Any questions on that there? So for thiols, you need to know the functional group. We're not going to do any naming or anything like that. You do need to know this reactions, both of them, the oxidation reaction and the reduction reaction. And